This is part 3 of relations and functions. In part 1, we discussed that there are several ways to show a relation or function or define it, and we did lots of relations in that one. In the second video, we discussed a little bit more about functions, and now in this video we're just going to expand on that. Remember, in a function, each input always has exactly one output. You could think of something going into a function machine and coming out as something else. And whatever you put in is called the input, and that is the independent variable. And whatever comes out is called the output or image, and that would be the dependent variable if we're talking about putting in an x and coming out a y. Now, often we're putting in actually the numbers, and so we'll get some ordered pairs for a function. Here are some relations, and let's determine whether each relation given is a function or not. If you want, you could try this on your own first by putting the video on pause. All right, let's look at the first one. So this is our x, and this is our f of x. Okay, so we see that the domain has 1, 2, and 3, and in the range there's just one number, 5. So when you look at it, does each input have one predictable output? And the answer is yes. So this is a function. Now, if you had two lines coming from the same number, then it would not be a function. All right, let's look at number 2. So you have a set of ordered pairs. Is it predictable if you put in one number, do you get exactly one output? And what do you think? The problem is right here. I've got 5 as the x value in more than one place with two different outputs. One time the output is 4, a different time the output is 1. So that is not going to be a function. All right, number 3. If the input is a person and the output is their mother, okay, so if you put someone in, out comes, let's say, the name of their mother or whatever, is that a function? Is it obvious? And actually, I should be kind of clear here. What I mean is their biological mother is what I meant. And in that case, yes, we each have exactly one bio mother. So this is yes. And let's look at the fourth one. The input, Henry VIII. Output, who he married. Well, he had a lot of wives, right? So this is not going to be a function. It's not predictable what name might come out, right? Which of his wives. Let's try a few more. Determine whether each relation is a function. These I've represented with graphs. So we're looking at the blue curve here. You got to decide if that's a function. For each x, is there exactly one y? Can you see a place where for a particular value on the x-axis there is more than one y value? And no, there is not. So this is a function. Okay. For instance, if I happen to choose right here, that's an x value, right? That's some value of x. I'll call it x1, whatever number that is. And this is exactly where the y value is. It's up that high. All right, let's look at this circle. Is the circle a function? For each x value, is there exactly one y? And no, actually, it's not. And here's why. Let's take this x value right here. That's some, I'll call that x2, some x value. Well, I've got two different ordered pairs, up there and down here. So this is not a function. And this leads us to something interesting if you're looking at a graph. What you can do is use what's called the vertical line test. If you're looking at a graph, if you can draw a vertical line and go through more than one ordered pair on the function, then it is not, on the graph, on the relation, then it's not a function. So for number 5, no matter where I draw a vertical line, I'll only go through the function once. But for number 6, I was able to draw a vertical line and pass through this relation in more than one place. So it's not a function. Now you could say, oh, but I could go over here. Well, it doesn't say that no matter where you put it. It says if there's any place that you put it that it's going to go through twice, then it doesn't pass what we call the vertical line test. So you need to pass the vertical line test to be a function. All right, let's go back a little bit and remember something about lines. Any non-vertical line can be written in the form y equals mx plus b. Hopefully you recognize this formula. M is the slope, b is the y-intercept. So this is an equation solved for y. Vertical lines are in the form x equals k. Notice there's no y at all, so you can't actually write it in the form y equals mx plus b. So just a little reminder, x equals 3. That means for all your ordered pairs, you've got 3 something. If you were going to write a little table of ordered pairs, 3, 3, 3, 5, let's see, 5, 4, 3, let's say. And now we're going to graph those. I would get 3, 5, 3, 4, 3, 3. We know from this table of values, or if I were to write these as ordered pairs, it's not a function because you see for this one x value input, there's more than one output, and also it wouldn't pass that vertical line test because the line itself is a vertical line. All right, so vertical lines are not in this form. All other lines are non-vertical, and so imagine no matter how you drew those lines, doesn't matter where you put them, they'll pass the vertical line test. So any non-vertical line is a function. Okay? So all non-vertical lines are functions. Okay? And in fact, it's called a linear function. So a linear function is a function that could be written in the form f of x equals mx plus b. So I'm using this other notation. Notice that looks like y equals mx plus b. Remember, often we interchange the f of x and the y. So a linear function really is just a line. That's what it means, right? This is what an equation of a line looks like. Y equals mx plus b, or f of x equals mx plus b. So now the question is, how would we graph a line, but if it's written in funny language, somebody might say, graph the function f of x equals negative 2x plus 1. Basically, what they're telling you is to graph a line. And in fact, if you ever see this function notation, f of x, this means it is a function. Because if you put an input in, this is the one with a formula, if you put some number in for the x over here on the right, you'll only get one particular number. So let's do that. F of x equals negative 2x plus 1. Just as a little reminder, how to graph lines. So we have the x-axis, the y-axis. The slope is negative 2 over 1, and the y-intercept is 1. So I'm going to go through 0, 1. My slope is negative 2 over 1, so I'm going to go over 1 and down 2. It's slanting the correct direction, or I could go to the left 1 and up 2. And all I'm doing is graphing the same line, y equals negative 2x plus 1. But what I could have done is actually get my ordered pairs by plugging in some values for x. So I could plug in, let's say, negative 1. That would be negative 2 times negative 1 plus 1, which is 3. Notice that's the ordered pair, negative 1, 3, that I see right up here. Right? Here's negative 1, 3. Okay. If I plugged in 0 for x, if you're plugging in 0, I get 1. So that's the ordered pair 0, 1 right here. And if I would have plugged in 1, I would have negative 2 times 1 plus 1. That is going to be a negative 1, and that's right here, the ordered pair 1, negative 1. So my input here is my x value, and what pops out is my y value of my ordered pairs. Okay? So that's why f of x, your y value here, your f of x really is just the same thing as your y value. Okay? All right, so this is just a little introduction to using function notation, and that's where you really think of it in terms of a formula, and then we're going to do some more using function notation on the next video.